Hello, Math 153. What we're looking at now is 11.7. We're talking about events involving and also conditional probability. The first objective is finding the probability of one event and a second event. How this is different is because now we're talking about two separate events. For example, you flip a coin once and then you flip a coin again. The next thing we're going to be doing is computing conditional probabilities. This is saying what's the probability of this happening if this already happened. So let's start with the first objective. Probabilities with independent events, and we're using the word and. So this is going to be your keyword is whenever you see the word and here. First thing we're talking about is independent events. What an independent event is, it's going to be the occurrence of one event that has no effect on the probability of another event. So that's what we're going to write here. An occurrence of one event, that has no effect on the probability of the other. Again, we're talking about two separate events here. This is saying it doesn't affect. Like I said before, the idea of flipping a coin. You flip a coin once. It doesn't matter if you get heads or tails. That's not going to affect the outcome when you flip the coin that second time. So the first idea we want to really look at is what is the difference between independent events versus mutually exclusive events. And we really want to make sure we can understand the difference between the two because they're easily kind of mixed up, if you will. Independent events, these are events that occur at different times. So independent events are events that occur at different times. We'll also see the kind of keyword, if you will, and with independent events. And we'll talk about the formula of that in a second. Whereas mutually exclusive, the key word we notice here is going to be the word or. And what these mutually exclusive events are, think back to the last section, is these are events that cannot occur at the same time. So events that cannot occur at the same time. Think of this as you can't flip a heads and a tails on one single flip. These would be mutually exclusive. And just as a review, mutually exclusive events, you'd take the probability of A or B, and we'd take this as the probability of A and add it to the probability of B. Now, let's jump down to in the box here below, we want to say, okay, if A and B are independent events, then the probability of A and B is going to be equal to the probability of event A occurring, and we're going to multiply it by the probability of event B. Again, these are if we have independent events happening. So this is going to be the formula that I'm going to fill in right up above. So the probability of A and B is going to be the probability of A times the probability of B. So these are the kind of the two formulas. You want to make sure you understand the difference. If you're talking about mutually exclusive, that's when you have to add the probabilities together. If you're talking about independent events, you want to multiply the probabilities together. So going off of the coin tossing idea that we briefly mentioned, if we wanted to find the probability of flipping a heads then a tails, we'd want to take the probability of flipping a heads and multiply it by the probability of flipping a tails. Well, we know with coins, the probability of flipping a heads is 1 out of 2. The probability of flipping a tails is 1 out of 2. 1/2 times 1/2 would be 1/4. Now, the first example that we're going to be looking at here. A family had 9 girls in a row. Find the probability of this occurrence. So we're talking about a family that has 9 children in a row, and them all being girls. So I'm going to start out by using the fundamental counting principle here. So we can say, okay, the first kid, the second, the third, fourth, fifth, sixth, seventh, eighth, and the ninth. Now we said that they had 9 girls in a row. Well, we know the two possibilities are a boy and a girl. So that means they had a 50% probability each time they had a child that it would be a girl. So each of these children, they had a 50%. So I just went through and made it 1/2 probability for each one. Now, using the fundamental counting principle, we know we have to multiply these all together, or we can think of these as all these separate events. The first event times the second times the third times the fourth, and so forth. So we have this 1/2 50% probability, and it's being repeated 9 different times. So you can type it in your calculator 1/2 to the 9th power to make it easier, and we get 1/512. That would be the probability of a family having 9 girls in a row. Okay, moving on would be like find the probability of this given that. Oops, looks like I to the next one. So now example 2, we're talking about hurricanes and probabilities. We're going to see examples here talking about storms and things of that nature. If the probability that South Florida will be hit by a hurricane in any single year is 5 out of 19, what is the probability that South Florida will be hit by a hurricane 3 consecutive years? So the first year, the second year, and the third year. Well, we know that the probability of being hit by a hurricane in any year is 5/19. So the first year, there's a 5/19 chance. The second year is a 5/19 chance. And the third year is a 5/19 chance. That's a 9. And then we have to multiply them all together. Again, if you don't want to type them all out separately, we can take 5/19 and raise it to the third power. Now, when you do this on your calculator, again, if you don't have your calculators out, you should have them out at this point, and we take the 5/19 and we raise it to the third power, you can see that we're getting a fraction of 125 over 6859. Now, here's where you want to be very careful with the instructions if it tells you to keep it as a fraction, or some of the instructions here will tell you to change it to a decimal. Let's say we want to round this to the nearest thousands place. We want to divide that out in the calculator. We'd get it's 0.018. So either of these would be appropriate. Just be very careful with what the question is asking you and how to answer. Now, the next way we'll see these is what is the probability that they will not be hurt by a hurricane in the next 10 years? So there's kind of 2 key words here. Now we're talking that they will not be hit by a hurricane over the next 10 years. Well, let's think about this. We know that the chance is 5/19 that they will be hit. So using the complements that we talked about in the previous section, that means 14 out of 19s means they will not be hit because together they create the 1. But we're talking about out of 10 years. So kind of working very similar to how we did the previous one, we want to take the 14 out of 19s is the chance that they won't be hit and raise that to the power of 10 because we're talking about 10 years. Now that's going to be a very, very small amount because we're raising it to the 10th power. So I'm just going to round that to the nearest thousands place again to get 0.0 and divide it out for 7. That's the probability that they would not get hit by a hurricane in the next 10 years. The next idea that we're moving to is talking about these and probabilities with dependent events. Dependent events is where one event depends on the next one happening. For example, if we're talking about the deck of cards, if you choose one card and do not put it back into that deck, that's going to change your probability with the next card that you draw. So dependent events, what we're going to write here is the occurrence of one event the occurrence of one event has an effect on the probability of the other. The formula here is we're going to take the probability of A and B is going to be the probability of A, and we're multiplying it by the probability of B given that A has occurred. So now we need to take into event that something already happened before we can look at probability of B. So now what this is going to look like. Let's go to the next example on the next page. What we're talking about here is saying you want a free trip to Madrid and you can take 2 people with you. Bad news is 10 of your cousins have appeared out of nowhere and want to go with you. So you write each of your cousin's name on a card and place those cards into a hat. And then you pick one name out. Then you choose a second name out without putting the first one back in. Let's see, if 3 of your 10 cousins speak Spanish, find the probability of selecting 2 Spanish-speaking cousins. So we know that we have to pick out 2 of our, we're picking 2 people here. So we need to find the first person that we're picking and then the second person. Now, it's also telling us that we want to choose Spanish-speaking cousins, and there tells us that 3 of our 10 speak Spanish. So that means the probability of picking a Spanish-speaking cousin would be 3 out of 10. So now we're saying we do not put their name back in because once you choose one, you're not going to want to reselect that cousin. But now we have to take into effect that we chose a Spanish-speaking cousin. So now there's only 2 Spanish-speaking cousins' name left in. And also, since we chose one out, there's no longer 10 cousins' name, but now there's only 9 cousins left back in. So now we multiply these together, and when we multiply fractions, we go straight across. So 3 times 2 over 10 times 9, which would be 6 out of 90, and we want to simplify this fraction to get a 1/15th probability that you will select 2 Spanish-speaking cousins. The next one, 3 people are randomly selected, 1 person at a time, from 5 freshmen, 2 sophomores, and 4 juniors. Find the probability that the first 2 people selected are freshmen and the third is a junior. So what we have to pay attention to here is that we are selecting 3 people. So we're going to say, okay, just like I did the first problem. So we're going to take the first person, the second person, and then the third person. We have 3 separate events. We know we're going to be multiplying these 3 events together. We also have to take into account how many people do we have total. We have 5 freshmen, 2 sophomores, 4 juniors. So altogether we have 11 people total. Now we want to find the first person is going to be a freshman. So we know we have 5 freshmen out of a total of 11 people. Okay, now we need to choose the next person. We already chose 1 freshman, so now we only have 4 freshmen left, and now we're down to 10 people to choose from. The third person, well, we know we're down to 9 people, but the third person we want to be a junior, and we know that we have 4 juniors, so that'd be 4 out of 9. And then we multiply across the numerators, which would be 5 times 4 times 4. And across the denominators, 11 times 10 times 9, which would give us, you can multiply and reduce. I'm going to do this all in one step. Multiply it together, reduce everything out, we get 8 out of 99. And you use your calculator to do this. If you type in the fraction template that we've looked at in class before, in the numerator 5 times 4 times 4, denominator 11 times 10 times 9, it'll give you that reduced fraction. Now, on to the second objective for this section is conditional probability. Now we're talking about the probability of an event B occurring, assuming that A has already occurred. The formula we're looking at here is the probability of event B occurring given that A has already occurred. Now, when we do this, we need to start with event A first. So we want to start with event A first. And we're going to be setting up a fraction with our event A is going to be our denominator, with event B is going to be the numerator. So how we're using this in a problem. Let's look at example 5. You are dealt one card from a 52 card deck. We want to find the probability of getting a heart given that the card you dealt is a red card. So to set up this problem, we want to start with the formula. We want to find the probability of getting a heart given that we chose a red card to start with. So again, like I said, you want to start with your event A first. So we want to think of a red card. How many red cards are there in a deck? We say, okay, out of the red cards or out of the deck of cards, there are 26 of the cards are red cards. Now what we want to think about is of those 26 red cards, how many of those 26 red cards are hearts? And we know that 13 of the red cards are hearts. So we set up our fraction as 13 over 26, which would be 1/2. So you have a 50% probability of choosing a heart given that the card you selected was a red card. The next one, we want to find the probability of getting a red card given that the card you dealt is a heart. So now we want to find the probability of having a red card given that we were dealt a heart. Well, think about it. Okay, how many hearts are there in a deck of cards? Well, in a deck of cards, there are 13 hearts. Again, always start with event A first. There are 13 hearts, and we want to say, okay, of those 13 hearts, how many of them are red? You think, wait a minute, all my hearts are red, so that would be 13 out of 13, which is 1, which means we have a 100% probability of getting a red card if we were dealt a heart. What you want to look for with these problems is this word given. Anytime you see that word given within your probability problem, that's when you know you need to set it up in this aspect. Okay, moving on to the last page here. We're going to be looking at a chart for the last 2 examples. When women turn 40, it's recommended that they undergo a screening for breast cancer. The table below is based on 100,000 women ages 40 to 49 who participated in the screening. And we're talking about the chart here lays out who had a positive mammogram, who had a negative mammogram, with who has breast cancer and who does not have breast cancer. And then it also gives us the totals there. I'd pause the video, make sure you're familiar with the chart, make sure you understand how the chart is laid out. Okay, now looking at this example, assuming that these numbers are representative of all the women ages 40 to 49, find the probability of the women in the age range, and we're starting with the first one. We're going to find the probability that they have a positive mammogram given, again, there's that keyword given, that she does not have breast cancer. Again, you always want to start with event A here. So we want to look at, okay, how many women do not have breast cancer? And we'd see that 99,200 women do not have breast cancer. So now we say, okay, of those 99,200, how many of them had a positive mammo? And we'd say, okay, of those, the positive was the 6,944. Again, we use our event B is our numerator here. So the 6,944 divided by the total amount that did not have breast cancer, which was 99,200. Now I'm going to convert this to a decimal to the nearest hundredths place, so I'm going to divide it out, and we get 0.07. On your homework, the instructions will be very specific about if you're answering as a decimal or a fraction. If it wants you to give a decimal, it'll tell you how to round. So now what I would like you to do, I want you to pause the video and try example B. So go ahead, pause it and try B out, and then when you're ready and you have an answer, unpause the video and compare it with what I have. Okay, you can see that we want to find the probability that a woman does not have breast cancer given, again, there's that keyword given, that she has a positive mammogram. So we start probability of no breast cancer given that she has a positive mammo. Again, always start with event A first. So we see that a total of 7,664 has a positive mammogram, and of those, 6,944 do not have breast cancer. So we set up our fraction and we divide it out, and I just rounded to my nearest thousands place to get 0.906. I know this video was a little bit longer. Hopefully all these examples kind of made sense. Watch it once or twice if you need to, and please reach out if you have any questions on anything. Good luck on the assignment, and we'll talk to you soon.